Hello friends. Again today we are going to discuss about bandwidth estimation techniques. So what are the bandwidth estimation techniques? Finding the minus 3 dB bandwidth of an arbitrary linear network can be difficult problem in general. So consider for example the standard recipe for computing bandwidth. Derive the input-output transfer function using node equations. For example, set S is equal to j omega. Find the magnitude of the resulting expression, and fourth one, setting the magnitude is equal to 1 by square root of 2 of the midband value, and for solve for omega. So what are the five standard recipes for computing bandwidth in sense? Derive the input output transfer function, set S is equal to j omega, find the magnitude of the resulting expression, set the magnitude is equal to 1 by square root of 2 of the midband value, and solve for omega. So the method of open circuit time constants. The method of open circuit time constants, also known as zero value time constants. This powerful technique allows us to estimate the bandwidth of a system almost by inspection, and sometimes with surprisingly good accuracy. And also open circuit towers identify which elements are responsible for bandwidth limitations to estimate the high frequency roll off point. This method is used. This method is used. What are the disadvantages of open circuit fires estimation techniques? Means it works only with poles. All poles should be real but not complex conjugate. No L and C together in the circuit. Okay. No inductance and capacitance should be togetherly used in the circuit. To begin development of this method, let us consider all pole transfer functions only. Such a system function may be written as V naught of S by Vi of S is equal to A naught by phi 1 S, phi 1 plus 1, phi 2, sorry, tau 1 S plus 1, tau 2 S plus 1, and up to tau n S plus 1. Multiplying out the terms in all the denominator leads to a polynomial that we shall express as bn s power n plus bn minus 1 s power n minus 1, and plus up to b1 s plus 1. This gives the equation number 2, where the coefficients b n is simply the product of all the time constants, and b1 is the sum of all the time constants. Okay, bn is the simply the product of the all the constants, and b1 is the sum of all the time constants, and b1 is equal to sigma I tends to n is equal to 1 into phi I. First order approximations. What are the first order approximations? Near the minus 3 dB frequency, the first order term typically dominates over the high order term, so that to a reasonable approximation we have. So what is that reasonable approximation then? V naught of S by Vi of S is approximately equal to A naught by B1 S plus 1 is equal to A naught by sigma I is equal to 1 to n phi I into S plus 1 into S plus 1. This gives the equation number 3. So the bandwidth of our original system in radian frequency as estimated by the first order approximation is then simply the reciprocal of the effective time constants. Okay. So second order approximation gives B2 S2 plus B1 S plus 1. Let us consider the denominator of the transfer function near our estimation of WH. Now at our estimated minus 3 dB frequency, the original denominator polynomial is phi 1 into phi 2 omega square h est plus j into tau 1 plus tau 2 omega h comma est plus 1, equation number 5. So equation number 1, 2, 3, 4, 5. Note that the magnitude of the second term is unity. As a consequence, both phi 1 omega h comma est and tau 2 omega h est must have magnitude less than unity. So the bandwidth estimate is usually conservative in the sense that the actual bandwidth will almost always be at least as high as estimated by this method. The new recipe is thus as follows. Now we are considered an arbitrary linear network comprising of only resistors, sources and M capacitors. Then the following components are there. Compute the effective resistance or J0 facing each JTH capacitor with all of the other capacitors removed. Open circuited, hence the method's name. B. Form the product tau Z0 is equal to or Z0 into Cj. The subscript 0 refers to the open circuit condition for each capacitor, and then sum all m such open circuit time constants. Tau J0 is equal to sigma j is equal to 1 to m or not Cj. The omega h comma estimation is equal to 1 by sigma j is equal to 1 to m into or j naught cj or j naught cj. Bandwidth estimation techniques. Now we are going to discuss about the method of short circuit time constants. So instead of estimating the high frequency minus 3 dB point, we want to find the low frequency minus 3 dB point of an AC coupled system. This dual technique is known as the method of short circuit time constants. In the method of open circuit time constants, we assumed that the zeros of the network were all at infinitely high frequency, so that the transfer function consisted only of folds. In the case of short circuit time constants, we instead assume that all of the zeros are at the origin and that there are as many poles as zeros. Thus, the corresponding system function may be written as V naught of S by Vi of S is equal to Ks power n by S plus S1 into S plus S2 up to S plus Sm, where the various pole frequencies may or may not be real, and where K is simply a constant to fix up the scale factor. Multiplying out the terms in the denominator leads to a polynomial that we shall express as s power n plus b1 s power n minus 1 plus up to bn minus x into multiplying out the terms in the denominator leads to a polynomial that we shall express as s power n plus s power n plus b1 s minus b1 sn minus 1 plus bn minus 1 into s plus bn. where the coefficients b1 is the sum of all the pole frequencies and b power n is the product of all the pole frequencies. Near the low frequency minus 3 dB breakpoint, the higher order terms denominate the denominator so that we can obtain that V naught of S by Vi of S is equal to Ks power n by S power n plus Bi of Sn minus 1 is equal to Ks by S plus sigma I is equal to 1 to n into Si. The low frequency minus 3 dB point of our original system in radian frequency as estimated by the first order approximation is then simply the sum of the pole frequencies, that is omega 1 is approximately equal to b1 is equal to I is equal to 1 to n Si is equal to omega L comma est. Before proceeding further, we should consider the conditions under which our neglect of the lower order terms is justified. Let us examine the denominator of the transfer function near our estimate omega L. For the sake of simplicity, we consider a second order polynomial with purely real roots S1 and S2. Now at our estimated minus 3 dB frequency, the original denominator polynomial is minus omega square L comma est plus j omega L comma est into S1 plus S2 plus S1 into S2. Substituting our expressions for the estimated minus 3 dB point, we obtain minus of S1 square plus S2 square plus 2S1 S2 plus j into S1 square plus S2 square plus 2S1 S2 plus S1 S2. The low frequency cutoff estimate is conservative in the sense that the actual cutoff frequency will almost always be as low as or lower than estimated by this method. Consider an arbitrary linear network comprising only resistors, sources, and M capacitors. Then compute the effective resistance or Js facing each JTH capacitor with all of the other capacitors short circuited. The subscript S refers to the short circuit condition for each capacitor. Compute the short circuit frequency. Sum all M such short circuit frequencies. By using short circuit time constant method gives lower frequency point, that is omega 1 omega L comma est is equal to j is equal to 1 into m 1 by rjs into cj. By using open circuit time constant method gives higher frequency points. Omega h comma est is equal to 1 by sigma j is equal to 1 to m into r j naught into cj. Okay friends, thank you.